Hello everyone and welcome to lecture 4. In this lecture, we will be looking at some more applications of the divide and conquer paradigm and see how powerful it is in reducing the running time of algorithms. Let us quickly review what we learned in the previous lecture. We saw three methods to solve recurrences. The first was the substitution method, in which we had to guess the solution of the recurrence and then work out the math to prove that it is actually true. Then we saw the recurrence tree approach and said that using this approach would help us obtain the solution of the recurrence with some sloppiness, of course. And the substitution method could then be used to prove the solution obtained using the recurrence tree method. Finally, the fastest and guaranteed approach was the master method, where we could solve the recurrences only of the form ATN B plus f of n for certain values of a and b. The solution is always in the form of theta notation when we use master method. The first example we'll be looking at is the binary search algorithm. Unlike the linear search that we saw earlier, where the array A was not necessarily sorted, in the binary search, we want to find the index I of the element in the sorted array A such that A of I is equal to the key V. For this particular sorted array A of length 7 and key value of 50, the binary search works as follows. In each step, we first find the middle element, which over here is obtained by adding 0 and 6 and then dividing by 2. Therefore, the index of the middle element is 3 and A of 3 is 35. We then compare 50 with 35. If they are equal, we return the index 3. But in this case, they are not. Since A of 3, which is 35, is less than 50, and we know that the array A is sorted, we can easily ignore the first half of the array and repeat the binary search only in the second half. So in each step, we reduce the size of the array or we reduce the search space by n half. In the next step, we see that now we have to find the middle of the subarray starting from index 4 to index 6. So the middle element would be 6 plus 4 divided by 2, which is 5, and the value would be 65. So we compare 65 with 50, and since 65 is greater than 50, we would discard the upper half. And that would leave us with one element, which is element at index 4, which is equal to 50, and thus would return index 4 as our answer. Now let us see how to formulate the binary search as a divide and conquer problem. In the first phase, which is divide, we find the middle point of the array A in constant time and compare the value at this point with the key V. The base case is when the middle element is the only element left as the subarray of array A. In the conquer phase, we then repeat the search in only one of the two half subarrays of A, since the array is already sorted. Finally, in the combine phase, we do not have anything to do for this particular search algorithm. So putting all these three phases together, we would obtain this recurrence, where theta 1 is when we find the key, and we would have t n half plus theta of 1 if we do not find the key and we keep recursing over the array. So this theta 1 over here is actually contributed by the first phase, which actually finds the middle point of the subarray. So the solution of this recurrence using any one of those three methods that we saw earlier would be theta of log n. This example is an interesting one because it applies divide and conquer in a slightly different manner. It is powering a number x, which can be an integer or a real value, and The power n, however, should be a non-negative value. So basically, we want to compute x to the power n. The first approach that would come to mind is just multiplying x n minus 1 times to itself. So therefore, we would have x times x times x times dot 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 times x, where we have n number of x's which are multiplied n minus 1 number of times. So this would give us a running time of theta n. But can we do better than this? The answer is yes. We can divide the power n into half in each division step until we reach x to the power 1. So if n is even, what we need to do is we only need to calculate x to the power n half, and we have to calculate this only once in a recursive manner and then take its square. If n is odd, then we calculate x to the power n minus 1 whole half and then take its square and then do an additional multiplication with x. Since the multiplication operation takes constant time and each subproblem has the same value and thus is required to be calculated only once, we would have the recurrence of the form Tn is equal to Tn half plus theta 1. The reason why A is equal to 1 is because we only solve for one subproblem, and the second subproblem has the same value as the first subproblem, and therefore we do not have to calculate for the second subproblem. That's why A would be equal to 1. And B is equal to 2 because the problem x to the power n in every step is divided into 2 halves. This theta 1 is the constant time for the multiplication operation. So using any of those three methods would give us a solution theta log n. Now let's go back to the Fibonacci numbers that we studied earlier. We know that given f of 0 is equal to 0 and f of 1 is equal to 1, for any I value greater than equal to 2, we can calculate f of I recursively as the sum of f of I minus 1 and f of I minus 2. Also, using the magical golden ratio phi, we can get f of I using this equation. The problem with this equation, however, is that for very large n values, the computation of f of I exhibits an exponential running time, which we want to always avoid. We would very much prefer a polynomial running time. So the question is, can we make the running time polynomial? Yes, one way to make it polynomial is by implementing the Fibonacci numbers in a bottom-up manner. And what does that mean? We are given f0 and f1. So we can compute f2 by adding f0 and f1, and then compute f3 using f1 and f2, compute f4 using f2 and f3, and do this until we reach fn. So for any I value, we can get f of I because we have already computed f of I minus 1 and f of I minus 2. So since we are doing it in a linear manner, this would have a running time which is linear, that is theta n. Up till here, we were able to reduce the exponential running time to a polynomial running time. Now the question is, can we make it logarithmic? Doing so would be great, right? Looking back at the examples seen so far in this lecture, can you think of a solution that would very likely give us a logarithmic running time? One solution may be using the golden ratio function of f of I, where we can use recursive squaring to calculate phi of I and phi hat I. Then, when we round to the closest integer, it would result in the Fibonacci number we want. The issue here is that phi is an irrational number that is a solution to the quadratic equation x squared minus x minus 1 equal to 0. So since floating point machines use a finite number of bits to store decimal numbers, squaring phi will result in round-off error and therefore will not always give the correct value for f of I. It is a logarithmic in terms of running time, which is great, but it is not an efficient approach. So what next? An effective recursive squaring method is to calculate not only f of I, but also f of I plus 1 and f of I minus 1 given in this theorem. So this theorem states that you can calculate f of n for any n by taking the nth power of this matrix. And since we are taking the power, we have already seen powering a number, so we can divide this into half and we would get a running time of log n. So now let's try to prove this theorem. So we use proof by induction to prove this theorem. We say that for the case when n is equal to 1, which is our base case, we would just have to plug in n is equal to 1 over here. And we see actually this is true. F of 0 is actually 0, f of 1 is 1, and f of 2 is 1. The next step is the hypothesis. And we say that we assume that this theorem is true for n minus 1. Therefore, for this matrix, we would have the solution. Now, based on this assumption, we go into the inductive step. So if it is true for n minus 1, we have to prove that it's also true for n, which is 1 more than n minus 1. So we would have this matrix, and this matrix can actually be written as this matrix, which is basically this matrix, times one of these matrices. So if you actually work out the math, that means you multiply this row with this column and you find the elements of this product, you would see that it actually is this. So we have this submatrix and we have this constant matrix. So this submatrix actually we can replace with this assumption that we made in the hypothesis, because we already assume that we know the solution is this matrix to the power n minus 1. So when we plug in this over here, so we are multiplying this matrix to the power n minus 1 times the same matrix, which would give us basically this matrix to the power n, and we prove our solution. So we use squaring, and with squaring, we can show that the running time would actually be theta of log n. The last example that we will be looking at today is a practical problem called the VLSI layout problem, where VLSI stands for Very Large Scale Integration, and it is a process of creating an integrated circuit by combining thousands of transistors into a single chip. Here, we want to place small chips on a grid in such a way that the chip occupies the minimum area, and this is a very common problem in microchip layout design. In our example, suppose we want to embed a complete binary tree, as shown over here, with n nodes on a given grid, as shown over here, such that the whole tree occupies the minimum area on this grid. The rule here is to place each node, or transistor if you may, at each grid point and connect them without crossing each other. So if you are asked to embed this given tree on the given grid, one solution would be as such. Over here, the red dots denote the nodes, and this red dot is actually the root of the binary tree. And the space that is left empty between the tree cannot be used elsewhere because it would cross the lining which connects these nodes. If we denote the height of the tree by h of n and we denote the width by wn, we observe that as we move down from the root, the number of nodes in each subtree reduces to n half. Therefore, the height of the tree is the height of the subtree plus 1. Pay attention that since the tree is a complete tree where the last level is filled with all leaves, the subtrees will have the same number of nodes. So if you look at the left subtree and the right subtree, they both have the same number of nodes, which is equal to n half of the total tree. Therefore, with this said, we would have the equation for h of n which is equal to h of n half plus theta 1, where a over here is 1 because of the fact that the left subtree and the right subtree are basically the same. And we have b is equal to 2 because in each step, the tree is broken down into two equal halves. And the theta 1 is the cost for adding this one extra height to connect the subtree to the root. We have already seen that the solution to this recurrence is actually log of n. Now, to write the equation for Wn, we would get this recurrence. Over here, note that a is equal to 2. And that's because every time the tree is broken down into two halves, each half occupies its own space along the width, which unlike the height, each half is actually placed in parallel or aside each other. Therefore, it doesn't add to the height. But along the width, each half actually adds to the width. And that's why we have a is equal to 2. And similarly, we would have the same equation, and the solution to this we know is theta of n. Therefore, the area that this tree occupies on the grid would be the product of h of n and w of n, which would be theta of n log n. Now, what we want to try is to try to further reduce the area that it occupies. That means to try to remove the logarithmic factor in the solution. And how do we do that? So if we want to make it linear, we have to come up with two functions such that their product would be actually a linear function. So what do you think? What two functions come to your mind that their product would be n? Let us consider square root of n, because we know square root of n times square root of n is equal to n. So if we take the two functions to be square roots of n, then using the master method, we know that the term log b of a should be 1/2. That means a should be equal to 2 and b should be equal to 4. So we would have n to the power log base 4, 2, which would be n to the power half, and that is equal to square root of n. Also, we know that we want this term to be the dominating term so that we could have such a solution. That means the f of n should be some function which is polynomially smaller than square root of n. That means it should be some function of this form where we would have n to the power half minus some epsilon value. Now let's look at the grid and let's look at another different layout that would be more efficient. This is a layout which is known as the H layout, and you can probably guess why, because we have placed 4 H's and connected them, which basically represents the same binary tree that we have seen. Over here, note that the height and the width are the same, and therefore we can replace them with another term called L of n. Unlike the previous case, we see that every subtree has actually n fourth of the total number of nodes in the actual tree. So we can actually rewrite this as L of n is equal to 2 times Ln fourth plus theta 1. A is equal to 2 because these two subtrees are placed next to each other, and similarly along the width, these two trees are placed next to each other, and therefore we would just have to consider 2 subproblems instead of 4. And each subproblem would have 1/4 the actual size of the total tree. And the solution to this equation would be theta square root of n using case 1 of master method. So we were able to reduce the area to theta of n by solving L of n as given over here. Therefore, the area would be ln times ln, which is equal to square root of n times square root of n, which is equal to n. Therefore, the minimum area would be of the order theta n.